Okay, so what we're going to do now is move on to one of the most important techniques for integration because it's very powerful, it's very flexible. It enables you to take a very complicated integral and turn it into something much more manageable. Often what we're going to wind up doing is taking it and turning it into something which enables us to use the power rule, but not necessarily. I mean, it can be used to do a lot of things, but ultimately, our goal is to simply take a very complicated integral and turn it into something more convenient. And the logic behind it, of course, as you can see here, is based on the chain rule. So, quick reminder, what is the chain rule? That tells us that if we have a composite function, f of g of x, the derivative of this composite function is equal to f of g. Actually, let me write it like this. The derivative of this composite function is written as f prime of g of x times g prime of x. That's better. All right. This is the chain rule. And we run into it quite frequently when we have composite functions. But so what essentially is happening here is that we're trying to take, like I said, a very complicated integral and using the chain rule, rearrange it into something which is easier to deal with than what we started out with. Now, the explanation of this, I think, is more involved than the actual technique itself. I mean, you can see this is how it's formally defined, but I think it would be easier to just start some examples and show you how this works. And when you see how straightforward it is, you'll say, "Oh yeah, this looks very promising." So let's start with an example. Now here you've got what appears to be an unbelievably complicated integral. Now, one thing you could do, of course, is you could actually span this term by raising this to the fourth power, but you would have a huge, huge number of terms. So maybe we should try something different. Okay, so what are we trying to do here? Well, let's go back to this introduction here. So we're assuming that there's some compound function. And so let's just say that we take this function and break it up into two pieces. Let's say this is our f of g of x, our compound function. And we're hoping that 6x dx, when combined, would represent g prime of x dx. Now, what that means is we have to figure out how to make this work. So here's what's going to happen. We're going to choose the letter u. U will be the letter that we use in each of these cases to represent g of x. So from now on, when you see u, just think of it as g of x, and then du dx would therefore be g prime of x. So you've got, if that's the case, then what you're actually integrating is f of u. And also here, if you notice, du would be g prime of x dx. So that means all of this can be replaced with du. So we have to think of this piece as a compound function of x. And the rest, whatever's left over, would be the g prime of x dx. So in this particular case, let's do this. Let's try this approach. And by the way, when you do this technique, you may not necessarily get it right the first time. You may have to go through a few trials or a little trial and error and find out what works and what doesn't. So the first thing we're going to do is rearrange this ever so slightly to make it a little more manageable. In particular, what I'd like to do is take my compound function and just get it to one side, and then over here I have everything else. Okay, so in other words, this looks like a good candidate for our f of g of x. This looks like a good candidate for g prime of x. So therefore, let's do this. Let's try u equals, remember u is a function of x. Let's let u represent 3x squared plus 4. If that's the case, then du dx, based on the power rule for derivatives, would be 6x. And that means that du would be 6x dx. So how does that help us? Because if you notice, let's go to the next slide. That being the case, so let me write this down again. We have 3x squared plus 4 to the 4th power, 6x dx. We've chosen u to be 3x squared plus 4, so that du is 6x dx. So this expression could be rewritten as u to the 4th power times du. And now it's just a simple power rule problem. All of a sudden you realize, oh, wait a minute. That's all I had to do. Now, of course, you have to replace that u with the original substitution for whatever function of x you chose. So in this case, you have 3x squared plus 4 raised to the 5th power over 5 plus c. Oh, well, that didn't look that hard at all. In fact, it's not hard, but the challenge is identifying which is which. So in other words, remember the whole point of all this is that you have an integral of a composite function and potentially the derivative. So you have f of g of x plus you have g prime of x dx. So you have to figure out which is the correct g of x so that you can make the u substitution and then turn it into something much more manageable. And by the way, in the next slide, we're going to prove that the derivative of what we just came up with does bring us back to the original function. Okay, so in other words, if I take the, and don't forget the derivative of c is just 0, so we don't even have to worry about it. So if I take that derivative, I'm going to wind up with, based on the chain rule, first of all, of course, as always, I move the constant on the outside. So in other words, I'm taking the derivative of this expression that we just came up with. The 0, actually, it's this expression, but the 0 represents the constant's derivative. So I've got the derivative of 3x squared plus 4 to the 5th power divided by 5. So I move the 1/5 on the outside because it'll be easier that way. And then remember how the chain rule works. We've got f of g of x prime, the whole thing prime, is f prime of g of x times g prime of x. So here, if you think of this as our g of x, that would indicate that f of x is x to the 5th. So that f of g of x must be 3x squared plus 4 to the 5th power, and that's fine. Now, what about the derivative, though? Well, we need a couple of things here. So we've got the 1/5. So the derivative of 3x to the squared plus 4 to the 5th is 5 times 3x squared plus 4 to the 4th times 6x. Because this is f prime of g of x. Okay, and you can see by the power rule, if this is our f of g of x, then the derivative of that is 5 times the value in parentheses to the 4th power And then we still need g prime of x. So since g of x is 3x squared plus 4, then g prime of x is 6x. And that's where this is coming from. And that's what we started out with. So you don't have to do this. This is purely optional to prove your results with the chain rule, but you might want to try it just to make sure you didn't make a mistake. Now, this is a very powerful technique. We're going to need a lot of practice, though, because, it's just, it doesn't, it takes a while to get used to what we're trying to do here. All right, so now here's another one. You can see that we've got a bit of a mess in our hands. So we're hoping that maybe substitution will work. Sometimes, by the way, this technique is called U substitution because you can see we use the letter U to represent g of x. So what do we have here? First, let's write it as any compound function we have should come first. And then what comes after, you see, so remember what we're aiming for is, as we saw earlier in the definition, here it is. Let me just copy that. Rather than writing it all over again, I'll just copy this. So this could be our f of g of x right here, because it is a compound function. And then we're hoping that this would be our g prime of x dx. So what that means is here we would allow our g of x, or u as we're going to call it, to be what's inside of these parentheses, x cubed minus 3. And then f of g of x would therefore be, or actually f of x would therefore be x squared. So that f of g of x is x cubed minus 3 squared. And that's what we have. And then as far as g prime of x is concerned, that would therefore be, based on the power rule, 3x squared. And so it appears that we do have what we're looking for. We do have f of g of x, we have g prime of x, and we have dx. So that means that what we're going to do here is to allow, as we figured, we'll define u, which is our function of x, to be the x cubed minus 3. Then du dx would simply be 3x squared. Or we can think of this as du is 3x squared dx. You're just multiplying both sides by this. So that means this could be rewritten as u squared du. Okay, if this is u, then this entire piece must be u squared. And du is 3x squared dx. Those give us du. And now you just have a traditional power rule problem. Okay, so then you remember u is x cubed minus 3, so we have this cubed over 3. And that's our final result. Oh my God. Now, keep in mind, this only works in certain cases. It doesn't always work. We need to have a compound function of some kind, and we need to have the correct g prime of x. Otherwise, this doesn't help us at all. Then we would try something else. Like, let's look. Now, here's another one. Now, how do you know which one of these could be considered the composite function? Well, I'm guessing that the radical x minus 1 is what we're looking for. By the way, if you get it backwards, let's say you misinterpret something here, you would discover that you're turning it into something even more complicated. And that's how you know you're going down the wrong path, because sometimes it's not that open and shut. What should be the choice of you? Sometimes it's very obvious and sometimes it's not. If you get it wrong, you'll know right away because you're creating an even bigger mess, basically. So like, let's try here, f of g of x. Actually, instead of writing it like this, I guess I'll write it like this, where g of x would be the x minus 1 and f of x would be radical x. Okay. So of course that indicates that f of g of x is this radical x minus 1. So g prime of x is dx. Now, you can see there's a problem here because we have see, this one's a little tricky, isn't it? I was looking ahead and I realized that this one has a twist. So let's keep going with this. If u then is this x minus 1, remember u and g of x are the same thing. The g prime of x, or du dx, is dx. I'm sorry, it's 1. Du is then dx. So what that means is this expression could actually be written as, if u is x minus 1, x must be u plus 1. So that means here we have u plus 1 in the numerator. Here we have radical u, and here we have du. Now, it may not be obvious right away, but we can solve for this one using the power rule, because it's not easy, but we can do it, because what you can do is divide each of these two terms by radical u, and then split it up into two separate integrals. So remember, radical u is u to the 1/2, so u over radical u is u to the 1/2, and 1 over radical u is u to the negative 1/2. And then we can solve each of these very quickly and easily with the power rule. So we'll have u to the 3/2 over 3/2 plus u to the 1/2 over 1/2, based on the power rule, because of course I'm adding 1 to the exponent and dividing by that same exponent. And with the negative 1/2, I'm adding 1 to the exponent, dividing by that same number. That's what we have here, but then this is very clumsy, so I'm going to rewrite this first term as 2/3 times u to the 3/2 plus 2 times u to the 1/2 plus c. And now all I have to do is replace the original substitution of u equals x minus 1. And this is my final result. Wow. And of course, you can always feel free to double check it if you want. Now, here's an interesting twist. It turns out that sometimes when we want to use u substitution like this, the holdup is usually whether or not we can find the appropriate du in our integral. If it's not quite right, but it's only different by a constant, then we can actually manipulate the expression and use essentially turn it into a form where it does contain the correct value of du. So what does that mean? All right, let's look at this one. So here, clearly, our compound function is the radical x squared minus 5, because we can think of f of x as radical x squared minus 5. And now, if that's the case, g prime of x will be 2x dx. Okay. So we let u be x squared minus 5. Du is 2x dx. Well, actually, what I should do is break this up into pieces. Sorry, this is just 2x. Du dx is 2x, but if you multiply both sides by dx, there you go. Now we're good. So look what happens then. Even if you rewrite this thing as radical x squared minus 5 x dx, you could think of this as u to the 1/2 power. But oh no, guess what? We don't have the proper du. We need 2x dx. So here's what we're going to do. This is our clever strategy. We're going to multiply and divide this expression by 2. So we don't change anything, but look what happens. You'll agree that I haven't changed anything by multiple. You see the 2 here and the half cancel each other out. But all of a sudden, I've got exactly what I need. I've got the integral of u to the 1/2 du. Now I can just use the power rule. So you can see this is we used our cleverness to rescue this problem. We're able to use the substitution method, even though the integral doesn't contain the correct du, but since it was only different by a constant, we were able to provide it ourselves. Anyway, once we do that, you'll see that we end up with, let's jump ahead a little, one integral of 1/2 u to the 1/2 is, keep the 1/2 on the outside. After integrating with the power rule, we have u to the 3/2 over 3/2. Or what's going to happen here, by the way, is you're going to simplify it by multiplying by 2/3, because that's the inverse of this denominator, u to the 3/2, which is then 1/3 u to the 3/2 power plus c, of course. And then remember that u is defined as x squared minus 5 from way, way back in the beginning. We chose u to be x squared minus 5. So we end up altogether with 1/3 x squared minus 5 to the 3/2 plus c. All right. So here's an interesting one. And again, you can kind of tell this might at least be a candidate for u substitution, because our composite function could be thought of as the x cubed plus 5 to the 9th, of which the f of x is x to the 9th, and g of x is the x cubed plus 5. G prime of x is 3x squared. Now, that means if u equals x cubed plus 5, du dx is 3x squared, du is 3x squared dx. So, first thing we want to do over here is rewrite this expression. And we recognize that we don't have what we need. We need a 3 in here. So let's rewrite this as 1/3 integral x cubed plus 5 to the 9th 3x squared dx. So suddenly we have what we need, 1/3 integral of u to the 9th du. And then we're all set because now we just use the power rule. And let's see. Obviously, the integral of u to the 9th is u to the 10th over 10. And plus c, of course. So we end up with u to the 10th over 30 plus c. Ultimately, we end up with this. So I think that the next time we meet, we're going to have to do a lot of practicing with this technique in particular, just because it's so useful and so powerful. It's going to come up quite a bit, especially in Cal 2, when you're going to use integrals quite often. It's a very powerful technique, but we definitely need some practice because, so far we've restricted ourselves to polynomial, but it could be used in many other cases as well. All right, so now that is, I believe we're done with section 5C now. Yes, okay. So now there's only one more section in this chapter, D. What we're going to do, of course, as you can imagine, is bring back our old friends, the exponential and logarithmic functions. We have to have rules for them too. So here we go. The integral of e to the x dx is just e to the x plus c, which makes perfect sense since, remember, the derivative of e to the x is just e to the x. Now, this one's a little trickier. A to the x dx, we need not just the a to the x, but we have to divide by the log of a plus c. Now, here you're actually doing that too, but log e, remember, is 1, so you don't see it here. But we do need to divide by that log a if the base is not e. So here's an example. And by the way, it may not be super obvious, but these also can be solved for with u substitution. And here's how that would work. So you could think of this, if you let u equal negative x, if that's what we're choosing, du dx is -1, du is negative dx. What you actually have here, then, is the integral of e to the u du, which we just got through seeing is e to the u plus c. So you just end up with e to the minus x plus c. Oh, wait a minute. Oh, sorry, I just realized I blew it here. I forgot one important detail. The negative yeah, the dx is negative. Sorry, that's my fault. I went too fast. This is negative. We don't have negative, do we? So here's what we have to do. We're missing a negative, so let's write it like this. Okay, much better, because now look what we have. Negative e to the u. Now this really is du. So now it will end up with minus e to the u plus c. Now we're good. That's much better. How about this one? So is this a candidate for u substitution? Let's find out. Let's try u equals minus 2x cubed. That means our derivative is minus 6 x squared. So du is minus 6x squared dx. So this expression seems to be missing a constant for our du. We need a -6. Okay, so let's write this as, first we multiply the outside by -1/6. That makes this du. This is e to the u. Okay, so we're all set. But the tricky part was the -1/6, recognizing that we needed it. So we end up with -6 e to the u du. And of course, the u itself was originally -2x cubed. So this is our final answer. How about this one? Like I said, there's so many. We'll definitely do some more practicing with these before we dive into chapter 6. Okay, now which one of these do you think we're going to use? See, this is the challenge. It's not always, like I said, obvious which one should be your u. And if you do pick the wrong one, you'll end up, either you won't have the du and you can't provide it. In other words, if you're missing an x or something like that, you can't just put it in there. The only thing you can do yourself is a constant. You can provide a constant if you need it, but that's all. If you're missing the du, that means something's wrong. Or if you're just making a bigger mess, then something's wrong. So why don't we try, let's try u equals 1 plus e to the x, because this is the only obvious composite function. So that would indicate that du dx is e to the x, or du is e to the x dx. So do we have what we need? It kind of looks like it. I'm just going to rearrange it slightly. Just so that it's clear that we have the square root of u du. So we end up with u to the 3/2 over 3/2 plus c, or 2/3 u to the 3/2 plus c, 2/3 u. Oh, sorry, we're replacing the u with e to the x. Oh, no, 1 plus e to the x, all raised to the 3/2 power, plus c. Okay, now that's written out better down here. That was a little tight, but here it is. Okay. Here's another interesting one. And again, remember the whole point of this, try to make sure that you're going directly for the compound function in order to find your u. So like here, for example, what do we do? All right, let's try. U is 3e to the x minus 2. Okay, and then du is 3e to the x dx. So do we have that, or do we need to supply a constant? I think we're all set except for the constant. Yeah, because all we're missing is the 3. So let's write this as 1/3. 3e to the x minus 2 squared. And don't forget, I've moved the e to the ex over here. So this becomes 3e to the x dx. All right. Now it's in a good form because you can see that it's just 1/3 times the integral of u squared du. This is all du. This is all u squared. So we'll end up with u we repeat that here. It's 1/3 integral u squared du, which is 1/3 by the power rule, u cubed over 3 plus c equals u cubed over 9 plus c. And u itself is, remember, we decided u would be 3e to the x minus 2 cubed over 9 plus c. Not bad. Now the next one's interesting because it's not it's a definite integral for the first time. So far we've only been focusing on indefinite integrals, but that doesn't change anything. We're still going to use the same techniques, whether it's definite or indefinite. So let's try this one. How about the integral from 1 to 2, e to the 1 minus x dx. So let's try u equal 1 minus x. So the du is negative dx. So yeah, we're missing the negative. So let's rewrite it. So that we actually now just have minus the integral of e to the u du, which becomes minus e to the u, but it's not, there's no c because this is evaluated from 1 to 2. And so we have to, of course, replace the u with 1 minus x. Okay, so what does that give us? You got to be so careful with those negatives. So we have minus e to the minus 1 plus e to the 0, which is just 1. So you could rewrite this as 1 minus e to the minus 1 or 1 minus 1 over e. Okay. So here we have another one. Let's try this definite integral, the integral of e to the 2x integrated between 0 and 2. So let's try u equals 2x. So that du is 2 dx. That means we're only missing a constant here. Okay, so the actual integral is easy because it's just e to the u du. Okay, But remember, the integration is with respect to x, so we have to make sure we replace that u. Don't put like e to the second minus e to the 0 or something like that. So first, replace the u with its definition, the one we chose for it. So in other words, half e to the u is equal to, u was 2x. Okay, so we'll have 1/2 e to the 4th minus 1, and then we can just leave it like that. Now, what's coming up next is an interesting application of what we're doing here. It's fun to see once in a while what you can actually do with these concepts. So now, what's happening here is that we're assuming that bacteria grow according to an exponential curve. And so here's what we're going to see. The growth rate is q of t. The quantity at time t is 3 to the t power. So an exponential function has the form f of x is ab to the x power. A can be thought of as the initial value, which in this case is 1, because there's an implicit 1 here. And B is 1 plus the growth rate over whatever time frame we're looking at. Okay, so that would be 2 in this case, and that means 200% per unit of time. So it turns out that we can figure out how many bacteria there are at any given time by taking an integral. In particular, if we start with 10,000, what we're going to do is see that the integral of this function is going to, the integral of 3 to the t is going to give us the number of bacteria at any given time. Because remember, the integral is a sum. So if our function looks like this, and let's say we're looking at this time, 0 to, I don't know, 10, this is what we're going to find. All right, now a quick reminder from the rules we saw a few minutes ago. The integral of a to the x dx is a to the x over log a plus c. So because here it's 3 to the t, we're using the same rule, only the variable is t instead of x. So you've got 3 to the t over log 3 plus c. So here's what we're going to need to do. We're being told that the function initially starts out at 10,000. We're going to think in terms of thousands. So what we're going to do here is actually solve for this constant. All right, so in other words, we know that the integral, we just got through establishing that this is 3 to the t over log 3, but with this constant. So the initial value means that we're at time t equals 0. Okay, t equals 0 is today. Remember what time frame you're looking at. 0, the time scale 0 means we're at today. So we know that q of 0 is 10. So we're going to set 10 equal to 3 to the t over log 3 plus c, where t has been replaced by 0. And then you can see algebraically, that means that 10 equals 1 over log 3 plus c. which is the same thing as saying 10 minus 1 over log 3 equals C. So in other words, we need a specific value. It's not enough to have a constant in our result. We're looking for the actual amount of bacteria at a particular point in the future. So since we now have the appropriate constant, that means that our function can be written as Qt is 3 over t log over log 3 plus the constant. So after 2 hours, or any number of hours for that matter, we can plug in a value for t and just solve it. And so in this particular case, if you plug in 2, all of that turns out to be approximately 17.282. And since we're dealing with thousands, that implies the bacterial colony after 2 hours will reach 17,282. So in other words, at time 0, there were 10,000 bacteria. 2 hours later, there were 17,282. All right. So so the rest of this chapter covers a lot more examples, but let's see. Let me just jump ahead and see if there's something different here. Oh, okay. We have to go over logs. I see what's coming up next. Oh, and then we're going to be looking at rational functions. And then it'll turn out even then we can use substitution if we choose it wisely. That's always the key to this, is using it wisely. So all right, I think we've been going long enough at this. I think we'll save the rest of it for next time. We'll carry on with the rest of this chapter, where we're going to find a lot more interesting examples of use substitution. And so by the time we're done here, we'll have had a lot of practice. But I think we'll still go ahead and come up with some more examples to practice with, because this is fairly complicated, but it's also very, very important. So we want to make sure everyone truly understands this. So we'll stop it right here, and I'll see you all next time.